My area of research is in fluid structure interactions, which involve an unsteady fluid force, such as air or water, interacting with moving or deformable bodies, such as wings. We understand gusts as being just puffs of air, but in the atmosphere you can have gusts of all different sizes and shapes. You can have unsteady flow going around a building in urban environments. And for light aircraft, for example, those become very difficult to navigate. So understanding how these changes in the airflow that exist, say around buildings or even just in general in the sky, how those interact with flying vehicles is very important to making sure they fly stably, as well as preventing failure. When I look at an owl, I see different features that can possibly reduce noise. And the big challenge of the past 80 years has been, how can we understand those features to reduce noise? How can we remove them from the owl and then translate that information to things as diverse as wind turbine blades or aircraft wings or even automobiles and parts of that? So we were not trying to take the entire owl with us to these devices. We're just trying to understand what makes them quieter and then maintain their performance, say lift and drag, that people work very hard to establish at these companies such as Boeing and Airbus, to then improve their design on the acoustics without detriment to their performance aerodynamically. Part of what we as engineers do is try to take the world around us, make sense of it, and then design appropriately for a certain goal. What's really great about that as an engineer is that I have a background in aerospace, I have a background in mechanical engineering, I have a background in applied mathematics. But I also get to work with biologists and folks who have a very different skill set. But it's really a lot to be learned by crossing boundaries with these folks and really get to the bottom of old questions and maybe new possibilities.